Okay, today we're going to focus on sound waves and integrate what we already know about waves into something new. So, some of this is review, some of this is new. It's all waves. So, the first thing we need to know about sound is what it is. So, sound, let me just hide this here. So, sound is a disturbance that travels through a medium as a longitudinal wave. So, let's break this down for a minute. We know that sound has to travel through a medium. This is called a mechanical wave. Remember, mechanical waves are waves that require a medium to travel, such as air, liquid, or solids. Sound is one of those. Sound has to travel through a medium, which means sound is a mechanical wave. Sound is also a longitudinal wave. Remember, longitudinal waves are waves that vibrate parallel to the wave energy. That means side to side. So in our picture over here, we see there are parts that are smushed together called a compression, and there are parts that are spread apart called a rarefaction. These pieces, compressions and rarefactions, make up our longitudinal wave. As the waves come out, the wave travels across, and the medium vibrates back and forth, which is why we call it a parallel wave. All sound begins with a vibration. Remember, vibrations are just complete back and forth motions of these waves. When the vibration starts, it causes the particles next to them to vibrate and carry on the wave energy. When we talk about sound, we want to talk about our three main properties that we're going to focus on with sound: speed, amplitude, and frequency. The first one we're going to talk about is the speed of sound. The speed of sound always depends on the medium it's traveling through. Sound will travel fastest through certain materials and slower through other materials. The speed of sound depends on the medium, and it travels fastest through a solid medium. Travels second fastest in a liquid, and it's the slowest in a gas medium. So solids are fastest, liquids are second fastest, and gases are slowest. So we can actually look at this chart, and you can see the speed of sound travels the fastest in a solid aluminum, and it travels the slowest in a gas of sulfur dioxide. So you can see the different speeds of different materials that sound is traveling through. Now, the reason this is because of the state of matter that it's in. If we remember all the way back to chemistry with our states of matter, our solid particles are actually really close together. They vibrate in place. This actually helps sound travel. Sound vibrates against each other, and it's easier to vibrate the next particle if they're closest together. So, in a material such as a solid, the reason why it travels fastest is because it's a lot easier for the particles to vibrate. It's a lot harder in a gas for the particles to bump into each other, causing a lot slower reaction for our particles to vibrate. Now, I know that's kind of hard to understand because you can hear me just fine, and my voice travels through the medium of air, gas. But you can really tell the difference when we spread out and you shout something across like a big football field. You can't necessarily hear it as fast as you could see their mouth moving. That's the kind of deal we're looking at. Um, this also works with temperatures. At lower temperatures, our particles are going to move a lot slower and they try to condense together, again, causing the particles to get closer together. It all depends on whether the particles are close enough to vibrate off of each other. So, in general, the speed of sound travels fastest through a solid, then a liquid, then a gas. Sound does not travel at all in a vacuum of empty space. That's because speed or sound is a mechanical wave. It has to have a medium, solid, liquid, or gas. It cannot go in space. The next property we're going to talk about is loudness. Now, I'm sure you already know what loudness is. It's how well something can be heard. If it's loud, it's loud. If it's quiet, it's hard to hear. But the thing we need to talk about is that loudness is related to the amplitude of the wave. Remember, amplitude is the height of the wave. So the higher the wave, the louder the sound. So if you look at my two images over here, I've got this cute little bird that is very quiet, and we can see the wave coming out of this bird is not a very high amplitude. Small amplitude means that it has a softer sound. It's quiet. This bird, on the other hand, is yelling quite loudly, and it's creating a wave with a high amplitude. The higher the amplitude, the louder the sound. Something else to know is that loudness is measured on a decibel system. So higher decibels mean it's a louder sound. Smaller decibels is a smaller sound. That's just kind of information that's interesting to know, not necessarily what you need to know. What you do need to know is that loudness is related to our amplitude. Amplitude is height. The higher the amplitude, the louder the sound. So, quiz time. Which wave is louder? If you picked the second wave, you are correct. The higher amplitude makes for a louder sound. Good job. The next one we're going to talk about is pitch. My musical kids, you guys will probably already know that pitch depends on the frequency of the wave. So, pitch is just how high or low something is sounding. The pitch of a sound depends upon the frequency of the wave. Remember, frequency just means how many waves pass a certain point within a certain time period. The more waves, the higher the frequency. The less waves, the lower the frequency. And this is going to coordinate perfectly with pitch. More waves means a higher frequency, therefore means a higher pitch. Low frequency, less waves, means lower pitch. So I know you can hear my musical instrument here, but now I'm going to actually explain a little bit about some musical instruments just for fun. So those of you that are in band or orchestra, or if you've never even been in an orchestra or band, you know that there are some instruments that are small and some instruments that are big. Think of an instrument that is generally a high-pitched sound. We typically think of like a flute or a piccolo or a violin. These instruments are high-pitched sounds because they are small. The smaller the instrument, the higher the frequency that they're going to produce, which makes them a higher pitch. Lower frequency instruments are instruments that tend to be really big, like a cello or a bassoon or a tuba. These instruments are really big because they produce or they will produce a lower frequency wave, causing it to have a lower pitch. So the size of the instrument will produce your different kinds of waves. So just remember that a high frequency means a high pitch, and a low frequency means a low pitch. Quiz time! Which wave has a higher pitch? If you picked the first one, you are correct. So we know that these have a higher frequency. We can tell these have a higher frequency because there's more waves in this little box. Less waves over here, which means this has a low pitch. And this one has a high pitch. Higher frequency, higher pitch. So while we're talking about pitches, we know that there's certain animals that can hear different pitches than we can. I'm about to give you a test that is going to tell you how old your ears are and explain a little bit about how humans can hear certain pitches while others can't. And then we'll come back and talk about what kind of animals can hear other kinds of sounds. So I'm going to switch over to our video, and this is going to give you a little hearing test. So check it out.
Ears tuned to high pitches are the first to
All right, interesting, huh? So, if you were lucky, then you were able to hear all of those. If you're like Miss DiMaggio, unfortunately, I can no longer hear the under 40, and I'm not over 40 yet, so that kind of worries me a little bit. Um, but these are sounds that if you have good hear cells, then you should be able to hear them. Our average person can hear the sound frequencies between 20 hertz and 20,000 hertz, which is what that was just kind of giving us a normal range of an average person. Some animals, like dogs and cats, can hear above our hearing range, and this is called ultrasound. So, dog whistles and things like that are sounds that we might not be able to hear, but animals like dogs and cats can. That's ultrasound, above our hearing. Some animals, like elephants, can hear below our hearing range. This is called infrasound. So some elephants actually communicate, or all elephants communicate using infrasound, so their enemies can't hear them. They use a sound below what normal animals and humans can hear, so they can communicate long distances. Above is ultrasound and below is infrasound. All right, so now we're going to get into talking about interactions of sound. Again, we've gone through these interactions. Now we're just going to apply them to sound specifically. So remember, reflection happens when a wave bounces back after it hits a barrier that it cannot go through. This is called reflection. In sound, a reflected sound wave is called an echo. Now, we've all heard echoes. Echoes is what happens when the sound hits something and it comes back to us. That's reflection. So, reflections usually happen when there's hard, smooth surfaces. These cause the sound to reflect. Soft and bumpy surfaces like people and furniture don't really reflect sound well. Instead, they absorb sound. So that's why if you're sitting in a room or in your house, you're not hearing yourself echo. That's because all the squishy things like you and your furniture and your parents, all these things are absorbing the sound. So there is no echo. But if you're in an empty room, like an empty gym, or maybe you just bought a house and it's got no furniture in it, the sound can actually bounce off these walls because there's nothing for it to absorb the sound. So then it causes an echo. So the hard, smooth surfaces will reflect the sound, causing echo, and soft and bumpy surfaces will actually absorb the sound, resulting in no echoes. Now, some animals, like bats and dolphins, actually use reflected sound, echoes, to communicate with each other and to look at things around them. So, what they do is they send out what's called echolocation. They send sound waves out, it bounces off like food sources or barriers, and it bounces back and it gives them an image in their brain. So, they use this echolocation of a returning sound wave to be able to see. Military actually uses this as sonar for their submarines and even their aircraft, where they can send out sound, hits an object, and it bounces back so they can tell that where other things are. So it's pretty useful. Doctors actually use ultrasound waves, waves that we are above our hearing, to send into people's bodies, not just pregnant people, to see different things on the inside of our bodies, like a baby. It bounces off the baby and it comes back to us. No harm is done to the organs or the baby inside, but it gives us a clear picture of what's happening by using reflected sound. So reflected sound is actually a really cool interaction of sound. The next one we're going to talk about is diffraction. So remember, diffraction is when a wave bends around a barrier or through an opening. This is called diffraction. Sound waves can travel around corners or through gaps to allow us to hear things that we might not be able to see. So my class and Mr. Polk's class actually did this little demonstration by opening up our doors between our classrooms, and my class was able to hear Mr. Polk talking even though they couldn't see him. And Mr. Polk's class could hear me or hear my class even though they couldn't see us. That's because our sound went through the opening and around a corner. That's diffraction. So diffraction sound is just we can hear things without seeing them. It makes it pretty useful to figure out who's around that corner. The next two interactions are interference. Interference is a combination of two or more waves to form a single wave. And we have two types. We have constructive interference and we have destructive interference. Constructive interference happens when our compressions of one wave overlap with the compressions of another. In other words, we're making a bigger wave, which means louder. So remember, when we talk about loudness of sound, the bigger the amplitude or the bigger the wave, the louder the sound. Since constructive interference is the combination of waves making a bigger wave, this is going to make a bigger sound. And this happens when we break the sound barrier. So in this demonstration, we have this jet here, and it's showing you that all the waves are combining and crashing on each other. And when we break the sound barrier, you get something that's pretty loud. Destructive interference is the exact opposite. It makes sounds softer or cancels them out altogether. So destructive interference happens when a compression and a rarefaction overlap and cancel each other out, or makes it quieter. Your noise canceling headphones do this for you. So in a noise canceling headphone, the incoming wave, the noise around you, is hitting your earphone, and then the earphone is coming up with a wave, taking it, reversing it, and canceling it out so it doesn't actually reach your ear. That's why they're so expensive, because they have to shoot out the reverse of that wave so that it can cancel out and make it a flat line. It's actually a pretty cool technology for your sound. That is all the notes for 8th grade on-level, advanced, and tag. However, if you are a high school science student, you need one more thing to be complete with your notes. So if you're 8th grade on, tag, or advanced, you are done with your sound lecture. High school, stay tuned. All right, high school, you also need to know about the Doppler effect. So the Doppler effect is the apparent change in the frequency of a sound caused by the motion of either the listener or the source of the sound. That's really actually kind of confusing. What the Doppler is, it's a moving sound source. So as this fire truck, I'm using this as a demonstration, as it moves, it's kind of squishing all of our sound waves close together. When it's moving fast, these sound waves get squished together and they make a higher pitch because they're occurring at a higher frequency. So it seems like the pitch is higher in front of the fire truck because the sound is moving, causing the sound waves to smush together. However, when the fire truck passes you, these waves back here are being spread out because they're trying to play catch up. And they're trying to catch up to our moving source. But because these are further apart, their frequency is less, which means their pitch is going to appear lower than what it really is. The siren itself is actually not changing. It's one siren. But the reason why it sounds different is because it's a moving source. The waves in front sound higher because they're smushed together, and the waves in the back are more spread apart, so they sound lower. Let's check it out. So I'm going to come over here, and this is a fire truck demonstration. So you'll hear the fire truck coming toward you, and then as it passes the observer. So here we have the siren. It's moving toward us, so it sounds pretty high-pitched. So as soon as it passed us or passed the observer, it immediately changed like it was going a lower pitch. So it wasn't actually changing pitches. It's the same siren, but it appeared to change pitch because of the moving source. So instead of it just one sound, it kind of had a high and then a low pitch, kind of like a kind of sound. So that's the Doppler effect. It's the apparent change in frequency because of the motion of the observer or the source of the sound. And that concludes the sound lecture for high school students.